Hello my friends, welcome to our discussion on thermochemistry. So today we're going to be talking about heat, temperature, and thermal energy. We're going to distinguish between those three things, and then we'll also talk about the specific heat of water and also the specific heat equation. Let's get to it. So heat, temperature, and thermal energy. Temperature, as we know from previous units, is the average kinetic energy of all the particles. Whereas thermal energy is the total amount of kinetic energy of all the particles. So in temperature, you're taking an average of them, and in the thermal energy, you're taking the total amount. So you're just adding them all together and never dividing by anything. So what I think of is if we look at the average of all the weights of all the high school students in our high school, we take the average of that, and we compare that to the average weight of all the high school students in the whole country, what we would expect is there to be a roughly equal between those two averages. They should be about the same. Whereas if we took the total weight of all of our high school students and just added it all up, and we compared that to the total weight of all the students in the entire country, well, gosh, we would expect the country total to be really high because there's just so many more people in the entire country than our high school. And that's the difference between the temperature and the thermal energy. The average does not depend on the number of people, whereas the amount of thermal energy does depend because it's a total amount of all of them. Right? All right, that's good so far, I hope. We'll do more with temperature and thermal energy in the next slides. So let's take a look at this. So this is David. He's pouring a cup of coffee from a large coffee pot. And the question is, how does the thermal energy in the two things, the small cup of coffee and the large coffee pot, and the temperatures compare? So let's take a look at them. Let's draw a really quick diagram. So we've got here a coffee pot, and it's like a big coffee pot. And it's got a big handle here so you can pour stuff. I don't know, fly in my face. It's weird. And I have a large amount of coffee here. So, woo, all this is coffee. And then I have a small coffee cup over here. It looks like that. That looks fantastic. And it's got a small amount of coffee here. So compared to this amount, it's a small amount of coffee here. And the question is, how should the temperature compare? Well, it'd be really strange if when you poured out a small amount of coffee, you poured it out like cold because it was like less of it. That would be really strange. That's not the case. So when you pour a small amount of coffee out, you pour out hot coffee. So the temperature here is the same. So the temp is the same. And that's because the average kinetic energy is the same. All right? Now, thermal energy is a little different because it's the total amount of kinetic energy of all the particles. If we add up the kinetic energy of all the particles in the coffee, is a lot of particles. There's tons of particles in there. So the thermal energy here, I'll abbreviate that TE, the thermal energy on this side is huge because it's the sum of all these particles. Whereas the thermal energy over here, there's just fewer stuff. If we were to add these together, we would find a small thermal energy, right? So here, lots of energy inside this thing. Here, not much energy. One other way to look at that is thermal energy is the energy that you'll use to do things with. So like if you wanted to melt a bunch of ice, which is a weird thing to use coffee for, but let's say we're going to do that. Which of these two amounts of coffee would be better at melting a lot of ice? So if you're trying to like melt the ice off the stairs or something of your house. No, I know, bizarre thing to use coffee for, whatever. If you poured just this cup on here, it wouldn't melt very much ice. But this pot has the potential of melting a lot of ice because of all this thermal energy in here. All right, so another weird thing is David has this option to have one of these two things poured over his head. I don't know if he's made somebody angry or what's going on, but so which one should he choose? And here he should choose cup every time if he doesn't want to get burned badly because it has less thermal energy. Now down here you might initially think, oh, but they have the same temperature, it won't matter. Either way, they're going to hurt a lot. And this one is going to, they're going to both hurt a lot, but this one's going to hurt a lot less because it's going to give less energy into his body. It has less energy to give to his body as heat. All right. So far so good, I hope. Hope that's clear. Fantastic. Let's try this one. So once you ignite a spark, like on the 4th of July, those little sparklers that you go around, they burn at like 1,000 degrees Celsius. And all those little sparks that come flying off all over the place are at 1,000 degrees Celsius. But when they hit your hand, they don't burn you. It's like you just feel them hit, and it's like, well, I didn't even feel that hardly. The question is, well, why is that? They're 1,000 degrees Celsius. Why don't they burn you really badly? And the answer to that is they don't have much mass. So that little thing that's burning, that little spark that's burning is like here. It's like that little bitty thing that's like, shoo, I'm really bright. And I'm at 1,000 degrees. Temperature really is 1,000 degrees Celsius. So it's not that they're cooling off as they come to you, because when they hit you, they're glowing red hot. There just isn't much energy here. The thermal energy is really low. Let's say the mass here is something really small, like 0.001 grams. And that means the thermal energy is really small. Each particle is moving really fast, but there aren't very many particles, so there's not much energy transferred to your hand when it touches you. Whereas if you were to have a mass of it, let's say you have like a chunk here of this sparkler stuff fall off and hit your hand and it's all burning, it's like burning crazy, its temperature is still equal to 1,000 degrees Celsius. It's not hotter now that it's a bigger chunk, that the mass now, let's say the mass is 1 gram instead of 0.001 grams, so 1,000 times more mass. So its thermal energy here is huge. They're all moving really fast, and there's a bunch of them, so there's a lot of energy in there. So it's really big here, really big. This one is a bad burn, bad burn. So far, so good. So thermal energy is the total amount of kinetic energy in all the particles together. So now heat. Heat is super tricky. Heat is used wrong even in sciences a lot, and I'll probably even use it wrong a few times too. So heat is oftentimes used to refer to thermal energy. So you'll ask, how much heat does something have? And that's actually a bad way or an incorrect way of thinking about it. Heat is really just reserved for transfers of energy. So if something gains energy, its change in thermal energy, how much it gained, is called heat. And just like if it loses energy, it's also called heat. But the amount that you have isn't technically called heat, it's called thermal energy. Quick example here. So if we have an object that starts with 100 joules of thermal energy, that is not its heat. 75, then it cools off to 75 joules of energy. Again, this number is not the heat. This number is. The heat is how much it lost. So heat is always a transfer of stuff. If you want to know how much thermal energy you have, we refer to the term thermal energy instead of heat. Although, like I said, it's oftentimes used wrong and heat's used that way. But it's not really terrible. If you make that mistake, I wouldn't stay up late at night trying to fix it. All right. So on this one, let's do this. So we've got these 5 beakers here, and I want you to rank them from lowest temperature to highest temperature, and then separately from smallest amount of thermal energy to largest amount of thermal energy in each beaker. So go ahead and do this. Hit pause on the video, and then we'll talk about the answers in just a second. All right, awesome, you're back. Let's do this thing. So when we rank these from lowest temp to highest temp, remember temperature has it doesn't depend on how much stuff you have. So don't let the volume of things mess you up. The lowest temperature ones are the ones at 25 degrees Celsius. So I'm going to rank these right here. A, B, and E. They're tied for lowest, even though they have different amounts of stuff. Then the next highest temperature is this one, 50 degrees Celsius. Sorry, that's letter D, and then followed by letter C at 75 degrees Celsius. So temperature is about average energies and not about the total energy. So the number of things doesn't really matter. All right, so now we come down here to the smallest thermal energy. Now this one is trickier because it depends on how much stuff you have and how hot that stuff is. So let's look. The way I like to approach these problems that are really complicated, these ranking problems, is I start with one of them, and I'm going to say, we'll just start with A. It doesn't matter. I'm going to put A up here out of the way. and I'll put it right in the middle of this white space, and then just start ranking them on either side until I figure out what order they go in. So if I start there, I'm going to look over here and say, okay, so look at B. B is the same temperature. So if I was just looking at temperature, I'd say, okay, it's totally the same energy. Problem is, it has twice as much stuff. So if I were to add up the kinetic energy of all the particles in this bottom 25 milliliters, I would get the same total energy, the same thermal energy as this 25 milliliters. But then I have to remember, I have to add up all the energy in the top 25 milliliters as well. So it's twice as much thermal energy. So really this one is equal to 2 times A's thermal energy. So this is twice A. So way over here I'm going to put B because it's twice as much as A. And I left some space in case some of these other ones go in between. I don't know where they go yet. Now I come here to this really tricky one. I notice at first, oh my gosh, all right, so 25 degrees Celsius is 75 degrees Celsius. Well, that's 3 times hotter. So it should be 3 times the thermal energy of A. But then I notice, wait a second, it has less water. In fact, it has 2.5 times less water. So that's going to tend to decrease its thermal energy it has because there's fewer particles. So it would be divided by 2.5. So if I took the thermal energy of A, multiplied it by 3 for the temperature change, and divided by 2.5 by the less water, I'd end up with just a little bit more, 3 over 2.5, just a little bit more than A, but definitely less than 2 times A. So I'm going to put C here between these two. Again, I left space for the other ones that they go in between. I don't know where they go yet. All right, so far so good. Now I look here and I say, okay, so this one has twice the temperature change, right? So I'm going to say, hey, 2 times A. So twice as much temperature change as A. And then here, ooh, the volumes are the same, so that has no impact. This one really just has 2A. And notice B had the same. So I know that D and B are going to be tied. Right there. All right, so last thing to do. I come over here and I notice, okay, so this one is, the temperature is the same. So I'm like, okay, so it's the same as A. But then I'm like, no, wait a second. It has less water, so it's going to have less thermal energy. So it's 2.5 times less, so it's going to be A divided by 2.5 is going to be the thermal energy. And of course, that means it's less than A, so this one goes over here by E. And now I know my order. I'm going to go EAC and then DB tied. So EAC BD tied. Awesome. Let's do the next ones. So the specific heat of water. So there's this really cool idea called specific heat. And basically what it does is it tells you how many joules of energy are required to heat 1 gram of something by 1 degree Celsius. And this number can be really hard to work with because instead of just being like something per gram or something per degree Celsius, it's something per gram and per degree Celsius. It's like a ratio of 2 things. Well, it's like a ratio of 3 things, I guess. And it can be written, it's usually written just like this down here at the bottom. So it's summarized this way. 4.18 joules of energy it takes to heat 1 gram, 1 degree Celsius. So for every 1 gram and 1 degree Celsius you want to heat up, you got to go 4.18 joules of energy put in. So the amount of energy it takes to heat something up depends on how much temperature you want to heat it and how many grams you have. Let's see how to use this. So we're trying to figure out how many joules of heat will be required to heat 23.5 mils of water from 22 to 39 degrees Celsius. So I'm going to look at the heat it takes in 2 ways. I'm going to look at it for the energy it takes, I should say, for the temperature change, and I'm going to look at it for the amount of water. So we're going to analyze it in these 2 different ways, not different ways, but we're going to analyze them separately. So temperature and amount of water separately. So I know this number, this awesome number of 4.18 joules for every 1 gram, 1 degree Celsius. Okay, so let's see how much it would take to heat up this amount of water. And since 1 milliliter of water is equal to 1 gram, that's only true for pure water, right? That is true. This just turns to gram then. So to heat up 23.5 grams, if I want to heat it just 1 degree Celsius, how much energy would that take? So I guess I'm going to start with the amount of water here. So if I have 23.5 grams, I know it takes 4.18 joules for every gram. So if I have 23.5 times more than that, then I add the 23.5 times more joules, right? Because that's joules per gram, degrees Celsius. And I notice here I multiply this and I say, okay, so if I want to heat my 23.5 grams by 1 degree Celsius, I need 4.18 times 23.5. And that means I need 98.23 joules. Notice here that the grams cancel. For every 1 degree Celsius, I need to do 98.23 joules. Now the reason it's so much more than 4.118 is because I have way more than 1 gram here. All right, so there's a new number. That's just the effect of the amount of water. So that's what it requires to go up 1 degree Celsius. But I'm not going 1 degree Celsius. I'm going from 22 to 39, and that's a change in temperature of 17 degrees Celsius, 17.0 degrees Celsius. So if this is the energy it takes to go 1 degree Celsius, I just multiply that. 98.23 joules per degree Celsius times my 17 degrees Celsius. And I find that that number is, and I have 3 sig figs in my answer, so I'm going to say 3 sig, or in my problem, so I'm going to say 3 sig in my answer, 1,670 degrees Celsius cancel. I'm left with joules. So that is my final answer. Sorry, I did it from right to left. I apologize. So all I did here is I analyzed the amount of energy it takes to raise up 23.5 grams 1 degree, and then how much it would take to raise that many gram, that up 17 degrees for that total energy. So to do this, I would need to add 1,670 joules of energy. All right. Now you might be saying, Mr. Hauser, there's got to be an easier way to do that than to do that separate analysis and kind of blow your brain on it. I want to show you that because I think it's conceptual and I want to in your brain that way. But there is a nice little equation that will help us. You've used this equation before. Q equals mc delta T. Q is the heat absorbed or released. So that's what the letter Q stands for. It's the energy absorbed or released, which when it's absorbed or released, we call that heat. M is the mass of the object. C is the specific heat of the object. So for water, it's that 4.18 number. For different stuff, it would be a different number. And that delta T is how much the object changes temperature by. All right? So let's do some problems using that. So let's see. Tiana notices a styrofoam cup of water that is 50 mils of water, and it heats up from 22.0 degrees Celsius to 28.7 when she throws in this hot rock, which I don't know where she got a hot rock from. Whatever, I don't know. The question is, how many joules of heat did the water absorb? So I'm going to draw just a quick sketch of what we have here. So we have a water here, right? And we've got a styrofoam cup, and we've got water in it, and this is 50.0 milliliters, which is equal to, of course, 50.0 grams if it's pure water. And we've taken this hot rock and we've thrown hot rock here. So hot rock. As the rock cools up, as the rock cools down, the water heats up, and the water goes from starting at 22.0 degrees Celsius, it goes up to 28.7 degrees Celsius. All right. So we know that our equation here is Q is equal to mc delta T, and we're talking about how much did the water absorb. So this C for this one is going to be the water C of 4.18 joules per gram degree Celsius. Our delta T here is going to be the difference between these two for the water. And again, everything's focusing on the water, not the rock right now. And 50 grams is our mass. And then we can figure out what our Q is. So we go Q is equal to the mass, 50.0 grams, times C, 4.18 joules per gram degree Celsius times the change in temperature, and I just did that in my head, of 8.7 degrees Celsius. All right, awesome. So we've got to find Q now. Plug these into our calculator. 50 times 4.18 times 8.7. That is equal to 1,818 joules of energy absorbed. Now, when I look at sig figs, I've got 3 sig figs here, 3 sig figs here, 2 here. So really, this should be expressed as 2 sig figs of 1,800 joules. And that's my answer. Now, that's how much energy the water absorbed, right? But how many joules of energy did the rock lose? So then how do we figure that out? And to do that, we have to remember back to conservation of energy. If one thing gains energy, the other thing lost it. So if this much energy was gained by the water, then this much energy was lost by the rock. So the rock lost 1,800 joules of thermal energy, of heat. All right, that's that one. All right, so in this comprehension check, what we want to do is we want to raise all these beakers of water up to 100 degrees Celsius here. So we have the same goal in mind of 100 degrees Celsius for all of them. The question is, which one's going to require the least amount of heat and which one's going to require the most heat in order to get them there? And heat's used correctly here because we're talking about how much energy is being added. So which one's going to take the most to least heat? Or sorry, least to most heat. So give this a shot real quick. When you're ready to see what the answer is, go ahead and unhit pause. So go ahead and pause the video now. All right, here we go. So first thing I would do in this problem is I'd look for anything that was obviously going to be the easiest one. And the first thing I noticed, though, is that these temperatures don't really help me much because I'm looking really for how much is the temperature going to have to change to figure out how much heat we're going to put in. To get this one to 100 degrees Celsius, I'm going to have to heat this water up by 75. So the change in temperature here is going to be 5 degrees Celsius. Here, the change in temperature is also going to have to be 75 degrees Celsius. Now here, this one's only going to be 25 degrees Celsius. All right, so I'm like, okay, so that may be easier. And this one's only 50 degrees Celsius because it only takes 50 degrees to get from 50 to 100, right? And this one, back to a big change in temperature. I've got to really heat this one at 75 degrees Celsius. Now, so how much heat you put in depends on not just how much you have to heat up by, how much temperature change, but also how much stuff you have. So first thing I'm going to do is look for something on here that I think might make it, might be the smallest or largest one on here. And when I look here, I say, oh, wow, look at this one. So this one has very little water in it and very small temperature change. That's going to be super easy to heat this up. It has the smallest volume and the smallest temperature change. And between this one, this has a bigger temperature change. There's going to be more. So I think C, I know C is going to be the smallest. So I'm going to go ahead and put C down here as the smallest. And I'll just start playing with the other ones. Now, if I can find something the opposite of that, so something, I know if we have a lot of water, it's going to be harder to heat up. It's going to take more heat and a big temperature change. So I'm looking for something like that. And sure enough, here's one. It's got a ton of water in it, and it's got a really big temperature change. That's going to be, it's got the biggest temperature change and the largest amount of water. That's going to be over here. That's going to be really hard to heat that one up. So far, so good. So we've got C and B knocked out. So let's go ahead and I'm just going to slash C and B, get those two slashed out. So now where does A and the rest of them go? So if I look here, same amount of water, but A is a bigger temperature change. So A is going to require more than D. So I know that D is going to go here, A is going to go here. The only question we have now is where does E go? Does it go in between them or before or after them? Let's look. Now on this one, we have 10 mils of water and we have 75 degrees Celsius. And that is going to be super tricky. So we have a big temperature change, right? and we have a small amount of water, so they're kind of working against each other. This is going to make it hard to heat up, that the small amount of water is going to make it easy to heat up. So this one compared to, let's say, A is, oh wait, so this shouldn't be too bad actually. This is the same temperature, right? Same temperature change, but 2.5 less water. So compared to A, this is just A divided by 2.5 times, right? So it's that many times less than the energy of A. So we know it's on this side somewhere, but we don't know if it's on this side of D or that side of D. So let's look at D real quick. Now this one says 50 degrees Celsius and 25 mils of water. So 50 degrees Celsius is less temperature change, so it should be easier. So, oof, this one's going to be rough to do this with this logic stuff. So the other way we can do is we can revert to just calculating the Q for each one. So, whoops, Q is equal to mc delta T. So the mass here is going to be 25 grams times, let's just call it 4 for both of them right now, just to make life a little easier. And then a change in temperature of 50 degrees Celsius. This isn't the true number, but it'll give us how big they are compared to each other. So 25 times 4 is 100, times 500 is 5,000-ish joules, right? It's a little more because this guy's a little higher. And over here, I'm going to do the same thing. So we're going to say this one is 10 grams times 4. That same rough estimate for that. And this one's 75 degrees Celsius. Whoops, 75 degrees Celsius. And so 10 times 4 is 40, times 75 is not 5,000. It's more like, I don't know, 3,000-ish or something. So E is less energy than D. So E goes here. And remember though, but C is even less. So this one goes C, E, D, A. Awesome. So in this case, there were no ties. Now you could have just done these calculations right here for every single one of them and then just put them in order from, you know, requires least energy, least heat to most heat. That's the other option of doing it. All right, awesome.